Imagine a highly skilled, incredibly secretive chef.
No, I like this analogy.
Right. So you give the chef a list of ingredients, they disappear into the kitchen, and an hour later, they bring out the most perfect, delicious cake you have ever tasted.
Sounds great so far.
Exactly. But when you ask for the recipe, they just cross their arms and shake their head. They absolutely refuse to tell you.
Yeah, that would be incredibly frustrating.
It really would. And for the last few years, this is exactly how artificial intelligence has been operating in the highest levels of scientific research. It gives us the cake, but not the recipe.
Completely. We get the perfect answer to a complex problem, but we have no idea how it was made.
Right, and you certainly can't make it yourself. You are totally dependent on the chef.
Which is a huge problem in science.
Exactly.
Hmm.
So today, we're welcoming you to a new deep dive into a single, groundbreaking piece of source material you brought to us. And I know you, the listener, you love finding those perfect aha moments without getting bogged down by a ton of jargon, so this is going to be fun.
It's a really fantastic paper.
It is. It's a 2026 paper straight out of Nature Machine Intelligence titled Meta-Designing Quantum Experiments with Language Models. It's authored by Soren Arlt and his colleagues.
And it's a game changer.
It really is. Our mission today is to explore how these scientists finally, essentially, force the AI to write the recipe down.
Yeah.
We're going to look at how they're using language models, not just to solve isolated physics problems, but to write actual human-readable computer code that uncovers the hidden design rules of the quantum universe.
Yeah, writing the rules out in code.
Okay, let's unpack this. Because to understand how revolutionary this actually is, we first have to understand the kitchen where the secretive chef has been working.
Right. And that kitchen is the highly specific and honestly, frankly, bizarre domain of quantum optics.
Bizarre is a good word for it.
Yeah, it really is. To understand the bottleneck these researchers were facing, we have to talk about the strange world of quantum entanglement. In quantum optics, researchers work with fundamental particles of light, called photons. Now, a photon can have different polarization modes. Let's simplify it a bit and call horizontal polarization mode 0 and vertical polarization mode 1.
So on the surface, that sounds a lot like classical computing, right? Like you have a 0 and a 1.
Right, exactly. It sounds like standard binary.
But because these are quantum particles, they don't have to pick just one state, do they?
Not at all. They exist in superpositions. So a single photon can be in mode 0 and mode 1 simultaneously.
Which is already wild to think about.
It is, but the real headache for physicists happens when you introduce entanglement.
Right.
This is when multiple photons are in a state where their properties are so deeply, deeply linked that they cannot be described independently of one another.
I think the classic example mentioned in the paper is the Greenberger-Horn-Zeilinger state, or the GHZ state.
Yes, the GHZ state.
Yeah, I saw that mentioned in the paper. If I'm understanding it right, a GHZ state involves a three-particle superposition where either all the particles are in mode 0 or all of them are in mode 1 simultaneously.
You've got it.
It's basically like having three separate coins flipping in the air and knowing that when they land, they will all magically show heads or all magically show tails exactly together.
That is a brilliant way to visualize it, yeah. Now, to actually create these highly synchronized, entangled states in a physical lab, researchers have to build incredibly complex experimental setups.
I can imagine.
They use things like probabilistic photon pair sources and beam splitters and phase shifters. And here is where we hit the massive bottleneck.
The combinatorial explosion, right?
Exactly. As you try to create states with more and more entangled photons, say, going from 4 photons to 6 to 8, the number of possible ways you could arrange the lenses and mirrors on your lab bench just explodes combinatorially.
It becomes too much.
It becomes an absolute nightmare to design these experiments manually. Human brains just can't track it.
Which makes total sense as to why researchers started leaning on AI in the first place. I mean, if I'm a physicist staring at a nearly infinite number of mirror configurations, I'm absolutely going to ask a machine learning algorithm to find the right one for me.
Anyone would, yeah.
And looking at the history of the field, previous AI approaches were actually pretty good at this, right?
They were very successful at specific tasks.
Right. An algorithm could design an experimental setup to give you a specific 6-photon state.
Yeah.
But the trap was, if you suddenly decided, hey, I actually need an 8-photon state now, you were entirely out of luck.
Completely back to square one.
Yeah, you had to take that computationally expensive optimization process and start it all over from scratch. The AI gave you an isolated solution for 6 photons, but not a general concept for how the system worked.
Like we said earlier, it gave you the cake, but not the recipe.
Exactly. But let me push back on this for a second, though. Let's put myself in the shoes of a very practical engineer.
Okay, let's hear it.
If the AI is already smarter and faster than us at finding that single isolated solution, why do we even care about finding a general rule?
Ah, I see what you mean.
Like, can't we just ask the AI to calculate the 8-photon setup, then the 10-photon setup, and just brute force our way forward forever? Why do we need the recipe if the chef works for free?
What's fascinating here is that the brute force approach actually hits a hard physical limit very, very quickly.
Really? Even for supercomputers?
Oh, absolutely. The paper includes charts tracking the FLOP count, the floating point operations per second required to compute these individual solutions.
Right.
And the computational cost does not just rise linearly as you add photons, it escalates exponentially. We are talking about reaching a point where even the most massive supercomputers on Earth simply fail to find a solution for larger systems.
Wow. So it literally breaks the computers.
It does. But beyond the staggering computational cost, there is a more profound, I guess, philosophical reason. Scientists do not just want a printout of an answer. They want to understand the mechanics of reality. A list of coordinates for mirrors and lenses on a table does not give you an understanding of why those mirrors and lenses actually work.
That is a great point. So because brute force literally runs out of computing power, and because we actually want to understand the universe, we need a paradigm shift.
Exactly.
And that perfectly brings us to the core innovation of this paper, which is meta design. Instead of treating the AI as just an optimization engine that spits out a single experimental setup, Søren Arlt and his team changed the goalpost entirely.
They completely flipped the approach.
Right. They took a sequence-to-sequence transformer model, which is the exact same underlying architecture that powers modern language models, and they trained it to output a meta-solution.
Yes. And in this specific context, that meta solution is literally just a human-readable Python program.
Which is wild.
It is. It outputs a specific Python function, which they refer to in the paper as construct setup n. This tiny program is essentially a blueprint generator.
Okay, so the n is the variable.
Right. As the system size index, which they call n, grows from n equals 0 to 1 to 2, and so on, this single piece of Python code can generate the specific experimental setup for an infinitely large class of quantum states.
That's incredible. They finally forced the chef to write down the recipe.
They really did.
But wait, I have to ask. If finding the physical setup for an 8-photon state is so computationally impossible that it breaks supercomputers, how on earth did they actually train this model?
That is the big question.
Yeah, because to train a transformer, you need massive amounts of data. And the paper says they created 56 million synthetic training samples using 50,000 CPU hours.
That's right.
How do they generate 56 million examples of something that is supposed to be mathematically agonizing to figure out? Wouldn't that take millennia?
That is perhaps the most brilliant trick in the entire methodology. They realize there is a fundamental asymmetry in physics and computation. It's very similar to calculus, actually.
Oh, okay, I think I see where this is going. Like the difference between taking a derivative and finding an integral.
Precisely. If I give you a mathematical function, taking the derivative is usually a very straightforward step-by-step process. You just follow the rules.
Right, you just crank the handle.
Exactly. But going backward, looking at a derivative and trying to find the original integral is notoriously difficult and sometimes totally impossible.
Yeah, it's a huge pain.
It is. Well, the researchers realized they had the exact same asymmetry with quantum experiments. Direction A to B, taking a target quantum state and trying to design the physical experimental setup that creates it, is the hard direction. That is the integral.
Okay, so that's the direction that breaks the supercomputers.
Right. But direction B to A is incredibly easy.
Let me make sure I'm getting this. Direction B to A means if you already have the code for an experimental setup, just running a simulation to see what quantum state it produces is cheap and fast.
Yes, exactly. Simulating a known setup is the derivative. It requires very little computational power. So instead of torturing themselves trying to solve the hard direction millions of times to create training data, they just heavily spammed the easy direction.
That is so smart.
They used simple rules to generate 56 million completely random Python programs representing random physical setups. They ran those random programs in a simulator to see what quantum states they spat out for system sizes of n equals 0, 1, and 2.
That is incredibly clever. So they basically generated 56 million random answers, looked at what questions those answers belong to, and then just flipped the pairs around for the AI.
That's it exactly.
They fed the transformer the sequence of 3 quantum states and told it, predict the Python code that made this. They built this artificial universe of 56 million cheap solutions, trained the model to navigate the logic of that universe, and bank on the fact that the logic would transfer to real, unsolved physics problems.
It is such an elegant solution to the data scarcity problem in scientific machine learning.
I do have a tech-savvy question about the model itself, though.
Sure, go ahead.
Because, we are living in an era of massive, publicly available large language models. OpenAI, Google, Meta, they all have these monstrous models with hundreds of billions of parameters.
Right, they're huge.
So why did this team bother building a custom 133 million parameter transformer from scratch? Why not just take something massive, like Meta's Llama 3, and fine-tune it for this task? Wouldn't a bigger brain do a better job?
You would think so, and the researchers actually anticipated that exact critique.
Oh, it did?
Yeah, they ran a side-by-side test. They tried fine-tuning a pre-trained Llama 3.8b model using a parameter-efficient technique called QLoRa.
And what happened?
The results were really surprising. The fine-tuned massive model failed to outperform their purpose-trained, much smaller 133 million parameter transformer.
Wait, really? The model that is a fraction of the size actually won? How does that even make sense?
It highlights something critical about applying AI to hard science.
Yeah.
We are not asking the model to write a polite email or summarize a novel or write a poem, right? This is a highly specific, symbolic reasoning task. The vocabulary is tightly constrained. It is mostly math, specific quantum state notations, and strict Python syntax.
Okay, yeah.
When you are dealing with absolute, rigid, logical structures, a smaller model trained exclusively on that specific logic from a blank slate can often navigate the space more effectively.
Oh, that makes a ton of sense.
Yeah, a generalized behemoth like Llama 3 has to constantly fight against its broader, fuzzier understanding of human language. It gets distracted by the vastness of its own training.
Like, it didn't have to unlearn conversational English because it was born specifically to speak quantum mechanics.
Exactly.
That actually makes a lot of sense.
Okay.
Okay, so the model is built, it's trained on short sequences of 3 quantum states where n equals 0, 1, and 2. Did it actually have anything new to say?
Yeah.
Because this is where the theoretical rubber meets the quantum road.
Oh, it certainly did. The researchers put their trained model to the ultimate test against 20 target classes of quantum states.
Right.
These were states compiled from previous literature, known to have exceptional properties for things like quantum simulations or quantum communication, but many were notoriously difficult to build.
Wait a minute. Looking at the breakdown here, for 16 of these 20 target classes, no general meta solution was known to humans at all.
Exactly, completely unknown.
Meaning no human physicist had ever figured out the universal recipe for these states. So if the AI gets those right, it isn't just looking up answers in its training data, it is actually doing original physics.
That is the exact threshold they crossed. Out of those 20 target classes, the model perfectly solved 6.
Wow.
It outputted Python code that generated the correct physical setups, not just for the training inputs of n equals 0, 1, and 2, but extrapolated perfectly to much larger systems.
That's huge.
It is. Now, 4 of those 6 were rediscoveries of known rules, things like the W state, the take a bell, and the third bell states.
Which is a great baseline, honestly. It proves the model isn't just hallucinating garbage, It can find the real math that human physicists took years to figure out. Here's where it gets really interesting. What about the other 2?
The other 2 were the genuine, unbiased discoveries of completely new physical design principles.
Yeah.
The first major discovery was the general spin-12 state.
Let's unpack the spin-12 state because the paper makes a huge deal out of this. Why was this such a white whale for physicists?
The spin-12 state is absolutely fascinating. In this specific entangled state, no 2 neighboring spin-ups appear in the ground state. It is a very highly ordered structural pattern.
Right.
Previously, the only way physicists knew how to create this specific class of entangled states was by using entire atoms in what are called Rydberg atom experiments. They relied on a physical phenomenon called the Rydberg blockade.
When a blockade means literally blocking something.
Essentially, yes. In atomic physics, if you excite one atom, its physical bulk and energy state actually prevent its immediate neighbor from getting excited. It is like an umbrella opening in a crowded elevator. Nobody standing directly next to you can open theirs.
That's a great visual.
Right. But light particles, photons, do not interact like that. They don't have bulk. They just pass right through each other. So nobody knew how to force light particles to mimic this complex atomic behavior.
Until the AI figured out the architectural workaround.
Exactly.
It translated a phenomenon from atomic physics into the language of light.
Yep.
And the second discovery was something called the Majumdar-Ghosh model, right?
Correct. The Majumdar-Ghosh model comes from condensed matter physics. It describes a one-dimensional chain of magnetic interactions where the next nearest neighbor interaction is exactly half the value of the nearest neighbor interaction.
Oh, wow.
Again, highly complex, previously unsolved for this kind of scalable photonic setup, and the AI nailed the blueprint.
Let's pause on that blueprint for a second, specifically that Python for loop the AI generated. This blew my mind when I was reading the source material.
Jeez, my favorite part.
What does Python code actually mean in a physical lab? When the AI outputs a for loop, what is a human scientist supposed to actually do with that?
Think of the code inside the loop as a set of instructions for a physical module on a lab bench.
Okay.
The code might represent placing one beam splitter at a specific angle, followed by one mirror, followed by a specific laser pulse.
Right.
The for loop basically tells the human scientist, take this exact configuration of lenses and mirrors, lock it in, and then just copy and paste that physical module onto the bench for every single new photon you want to add to the system.
That makes perfect sense.
The loop is the physical blueprint.
Human scientists can look at that highlighted block of code inside the loop, and they can literally read the physical design principle. The AI isn't just handing us a black box of answers. It is handing us a textbook it wrote itself.
Exactly.
It bridges the gap between machine optimization and human scientific understanding.
And that readability is what makes meta design a completely new era for AI in science.
But, as anyone who loves science knows, we learn just as much from what doesn't work as from what does. The model perfectly solved 6 out of 20 target classes. What happened to the other 14?
Analyzing the failures is incredibly revealing because it shows us the boundaries of the model's current reasoning. 6 of those 14 cases fall into a category the researchers call unexpected generalizations.
What does an unexpected generalization look like in practice?
It means the AI produced Python code that perfectly matched the first 3 states it was prompted with n equals 0, 1, and 2.
Okay, so it get the start right.
It did exactly what it was asked to do for the small systems.
Right.
But when the researchers ran that same code for n equals 3 or 4, the output deviated wildly from the intended target pattern.
This raises an important question. If the AI found a rule that matched the first 3 perfectly, why did it suddenly fail on the 4th?
It comes down to the inherent ambiguity of infinite mathematical sequences. Think about it this way. If I give you the sequence of numbers 2, 4, and 6 and ask you for the next number, you will almost certainly say 8.
Right, because I assume the underlying rule is simply add 2.
But the rule could just as easily be a complex polynomial equation, where the first 3 numbers happen to be 2, 4, and 6, but the 4th number is suddenly 42.
Oh, I hate when that happens.
Right. If you only have 3 data points to look at, there are multiple perfectly valid mathematical ways to continue the pattern.
So the model isn't a mind reader. It found a mathematical rule that perfectly fit the first 3 data points. It just wasn't the specific rule the human physicists had in their heads.
Exactly.
But the paper points out something wild about this ambiguity. They highlight a target called the Dick-1 state.
Oh, yes, the Dick-1 state.
The model outputted a pattern that deviated from the Dick-1 target for larger systems. But when they simulated the physical setups generated by the AI's quote-unquote wrong code, they didn't get garbage. They got entirely valid, structurally sound quantum states.
That is the beauty of training the model on 56 million valid physical setups.
It's amazing.
It internalized the laws of physics so deeply that even when it guessed the wrong mathematical rule for the specific sequence, it still guessed a physically viable rule.
Wow.
The researchers note that these so-called failed generalizations might actually be uncovering completely new, unexplored classes of quantum states that we didn't even know we should be looking for.
It is like trying to invent a new kind of blue paint, failing and accidentally inventing purple.
Exactly.
It is a beautiful mistake. But we should also address the 8 cases where the model outright failed. In 4 classes, it only matched the first 2 states, and in another 4, it only matched the very first state. Did the model just hit a wall?
Not exactly. And it is important to clarify that this isn't necessarily a failure of the AI's intelligence.
Okay, why not?
After analyzing the results, the researchers suspect that in some of these cases, it might actually be a physical impossibility.
Oh, really?
Yeah. Take the GHD 3D times GHD 3 state, for example, when they ran traditional optimization algorithms on it, they realized it is likely impossible to build the 6-particle version of that specific state using only the experimental resources they provided to the model.
Ah.
You would need additional ancillary photons that simply weren't part of the available toolkit.
So the task was rigged, physically speaking. It was asked to build a house out of wood, but only given nails,
Basically, yes.
which honestly makes me trust the model more. If it had confidently spit out an answer for an impossible physical setup,
Yeah.
we would know it was just hallucinating.
Exactly. It knew its limits.
Now, I have to ask, because you might be listening to this and thinking, okay, this is great for quantum optics, but I am never going to build a photon pair source in my garage.
Probably not.
Is this meta-design trick just a niche tool for one incredibly specific subfield of physics?
Not at all. To prove the versatility of their approach, the researchers took the exact same meta-design pipeline and applied it to 2 completely different domains: quantum circuit diagrams and quantum graph states.
Okay, so when we talk about quantum circuits, we are stepping away from physical mirrors and lasers and moving into the abstract logic gates of quantum computing, right? Things like Hadamard gates and CNOT gates.
Yes, the basic logical alphabet of quantum software.
Got it.
And quantum graph states are mathematical representations used in measurement-based quantum computation, dealing with abstract network topologies like linear chains, rings, and stars.
Okay, very different domains.
Completely different. And in both of these new domains, the team trained new, slightly smaller models, about 89 million parameters, using the same synthetic data generation trick.
And did it work?
It worked beautifully. The AI successfully discovered general Python codes that perfectly extrapolated for classes like the Bell, GHZ, and Majumdar-Ghosh states in circuits, and the linear, ring, and star states in graphs.
It proved the pipeline works regardless of the specific physics involved. You just swap out the vocabulary and the simulation tool, let it generate its artificial universe of synthetic data, and the AI can find the recipe.
That's the real breakthrough.
So what does this all mean? For you, listening to this, why does an academic physics paper from 2026 actually matter?
It's a great question.
It matters because we are witnessing a fundamental transition in our relationship with artificial intelligence. We are moving away from the era of the secretive chef, the era of AI, as an oracle that hands us magic answers we cannot verify or understand.
Exactly.
We are moving toward an era where AI acts as a translator. It is looking at the hyper-complex combinatorial realities of physics, and it is expressing those realities in a universal, readable language.
If we connect this to the bigger picture, the methodology outlined by Arlt and his team does not have to stop at quantum mechanics.
Right.
The authors explicitly note that this could be applied across scientific disciplines. Imagine using meta-design to discover the underlying assembly rules for new functional molecules in material science, or mapping the configurations of next-generation gravitational wave detectors.
The possibilities are endless.
The AI is learning to speak the structural language of the universe.
It is the ultimate tool for decoding complexity. Which leaves us with a pretty massive thought to chew on. For centuries, humanity has assumed that the fundamental language of the universe is traditional mathematics, continuous functions, differential equations, integrals.
Yes, that's been the assumption.
But if this AI is showing us that the deeply complex, chaotic realities of quantum mechanics can be perfectly expressed as a scalable 12-line Python for loop, maybe the universe isn't a continuous equation after all.
Wow.
Maybe it is an algorithm. Keep looking for the recipes behind the reality, everyone. We'll catch you on the next Deep Dive.